Yes, it is possible to add ground fault protection, abbreviated GFP, to an existing switch main. However, it depends on the specific switch main and the code requirements for your jurisdiction. The National Electrical Code, abbreviated NEC, requires GFP for electrical systems in healthcare facilities as specified in Article 517. Since the building was previously a nursing home, it may still be classified as a healthcare facility, even if it is being converted to condos. Pringle 1600 amp switch mains are designed for industrial and commercial applications, but they may or may not be compatible with GFP devices. To determine if the switch main is compatible with GFP, contact the manufacturer, Pringle, or a qualified electrician. If it is compatible, it will be necessary to install a GFP device. Examples of GFP devices include firstly, a residual current device, abbreviated RCD, secondly, a ground fault circuit interrupter, abbreviated GFCI, and thirdly, an equipment leakage circuit breaker, abbreviated ELP. The specific type of GFP device and its installation requirements will vary depending on the switch main and code requirements. If the switch main is not compatible with GFP, it may be necessary to consider other options, such as firstly, replacing the switch main with one that is GFP compliant, and secondly, installing a separate GFP device for each circuit. It is crucial to consult with a licensed professional engineer to determine the best course of action for the specific situation, including any structural modifications that may be necessary. The cost of installing GFP can vary depending on the type of device and the complexity of the installation. GFP devices can trip if there is any leakage current in the system, including from faults in appliances or wiring. Regular maintenance and testing are required to ensure GFP devices are functioning properly. Let's delve further into the considerations for adding ground fault protection. Firstly, understanding the applicable codes and standards is paramount. The NEC provides comprehensive guidelines for electrical installations, and Article 517 specifically addresses healthcare facilities. Even with the conversion to condominiums, the previous use as a nursing home might trigger specific requirements for GFP. It is vital to confirm with the local electrical inspector or a qualified engineer whether these requirements still apply. Secondly, assess the existing switch mains compatibility. Pringle switch mains are robust and designed for heavy-duty applications, but their compatibility with modern GFP devices needs verification. Contacting Pringle directly with the model number of the switch main is the best approach. They can provide detailed specifications and compatibility information. Alternatively, a skilled electrician with experience in industrial and commercial electrical systems can evaluate the switch main. Thirdly, explore the different types of GFP devices. RCDs, GFCIs, and ELPs all serve the purpose of detecting ground faults, but they operate on slightly different principles and are suited for different applications. An RCD typically monitors the current balance between the supply and return conductors. If there is an imbalance, indicating current leakage to ground, it trips the circuit. GFCIs are commonly used in residential settings and are designed to protect individuals from electrical shock. ELPs are similar to RCD but are often used in industrial applications. The choice of GFP device depends on the specific characteristics of the electrical system and the applicable codes. Fourthly, consider the installation requirements. Adding GFP to an existing switch main is not a simple task. It requires careful planning, skilled labor, and adherence to safety protocols. The installation might involve modifications to the switchgear, wiring changes, and the addition of new components. It's essential to hire a qualified electrician with experience in GFP installations. They can ensure that the installation is done correctly and safely. Fifthly, evaluate alternative solutions. If the existing switch main is not compatible with GFP, there are alternative approaches to consider. Replacing the entire switch main with a GFP-compliant unit is a costly option but might be necessary if the existing unit is outdated or in poor condition. Another option is to install separate GFP devices for individual circuits. This approach can be more cost-effective but requires careful planning to ensure that all circuits are protected. Sixthly, address engineering considerations. Consulting with a licensed professional engineer is crucial. An engineer can assess the electrical system, determine the best course of action, and provide detailed specifications for the GFP installation. They can also address any structural modifications that might be necessary to accommodate the new equipment. Seventhly, factor in the cost. The cost of installing GFP can vary significantly depending on several factors, including the type of GFP device, the complexity of the installation, and the labor rates in the area. Obtaining multiple quotes from qualified electricians is recommended. Eighthly, be aware of potential nuisance tripping. GFP devices are sensitive to leakage current, and they can trip if there's any leakage in the system, even if it's not a true ground fault. This is known as nuisance tripping, and it can be a major inconvenience. To minimize nuisance tripping, it's essential to ensure that all appliances and wiring are in good condition. Regular maintenance and testing can also help identify and correct any sources of leakage current. Ninthly, establish a maintenance and testing program. Regular maintenance and testing are crucial to ensure that GFP devices are functioning properly. The NEC requires periodic testing of GFP devices, and it's important to follow these requirements. A qualified electrician can perform the testing and provide documentation to verify that the GFP devices are working as intended. Tenthly, consider the impact on other systems. Adding GFP to an existing electrical system can have an impact on other systems, such as emergency power systems and fire alarm systems. It's important to coordinate the GFP installation with other trades to ensure that all systems are functioning correctly. Ground fault protection systems are designed to limit the duration and magnitude of ground fault current to protect equipment. These systems are typically required for service disconnects rated 1000 amps or more operating at voltages exceeding 150 volts to ground, but not exceeding 600 volts phase to phase. The requirement can be found in NEC section 230.95. A ground fault is an unintentional electrical path between a source of current and ground. This can occur when insulation fails, or when conductive materials come into contact with a grounded surface. Ground faults can be dangerous, causing electrical shock, fire, and equipment damage. The purpose of ground fault protection of equipment, denoted as GFPE, is to minimize damage to electrical equipment by limiting the amount of current and the length of time that a ground fault exists. GFPE is intended to protect equipment from the damaging effects of ground faults, while ground fault circuit interrupters, denoted as GFCIs, are designed to protect personnel from electrical shock. GFPE works by monitoring the current flowing through the electrical system. If a ground fault occurs, a portion of the current will flow through an unintended path to ground. The GFPE system detects this imbalance in current and quickly trips the circuit breaker, interrupting the flow of electricity. The tripping time is typically very short, in the range of milliseconds, which minimizes the amount of energy that can flow through the fault and cause damage. GFPE systems typically have a ground fault sensing device, which is a current transformer that encircles all the phase conductors and the neutral conductor, if present. Under normal operating conditions, the current flowing through the phase conductors will be equal and opposite, resulting in a net current of zero. If a ground fault occurs, the current flowing through the phase conductors will no longer be balanced, and a net current will flow through the ground fault sensing device. This net current is detected by the GFPE relay, which then trips the circuit breaker. GFPE systems are designed to operate with a time delay. This time delay allows the system to ride through temporary ground faults, such as those caused by lightning strikes. The time delay is typically adjustable, allowing the user to customize the system to their specific needs. The selection of a GFPE system depends on several factors, including the size of the electrical system, the voltage level, and the type of equipment being protected. It's important to consult with a qualified electrical engineer to determine the appropriate GFPE system for the specific application. The NEC provides guidelines for the selection and installation of GFPE systems. NEC section 230.95 specifies the requirements for GFPE on-service disconnects. The code requires that GFPE be provided on service disconnects rated 1000 amps or more operating at voltages exceeding 150 volts to ground, but not exceeding 600 volts phase to phase. The code also specifies the maximum clearing time for the GFP system. The maximum clearing time is 1 second for ground fault currents of 3000 amps or more. The NEC also provides guidelines for the location of the ground fault sensing device. The code requires that the ground fault sensing device be located as close as practicable to the source of supply. This is to minimize the amount of unprotected conductor between the source of supply and the ground fault sensing device. The installation of a GFP system should be performed by a qualified electrician in accordance with the NEC and the manufacturer's instructions. It's important to ensure that the system is properly grounded and that all connections are tight. After the GFP system is installed, it should be tested to verify that it is operating correctly. The testing should be performed in accordance with the manufacturer's instructions. Regular maintenance and testing of the GFP system are essential to ensure that it continues to operate correctly. The frequency of maintenance and testing will depend on the specific application and the manufacturer's recommendations. Typical maintenance procedures include visual inspection of the equipment, tightening of connections, and testing of the ground fault sensing device and the circuit breaker. Ground fault protection relays are also critical components of ground fault protection systems, offering advanced features and customization options for enhanced equipment protection. These relays are designed to detect ground faults and initiate a trip signal to the circuit breaker, disconnecting the power supply to the faulted equipment. Ground fault protection relays typically offer adjustable settings for pickup current and time delay, allowing the user to customize the protection to suit the specific application. The pickup current is the level of ground fault current at which the relay will initiate a trip signal. Time delay is the amount of time that the ground fault current must exceed the pickup current before the relay will initiate a trip signal. Some ground fault protection relays also offer advanced features such as harmonic filtering, which can help to prevent nuisance tripping caused by harmonic currents. Harmonic currents are currents that are multiples of the fundamental frequency of the power system, and they can be generated by nonlinear loads such as electronic equipment. Ground fault protection relays are typically installed in a control panel or switchgear, and they are connected to the ground fault sensing device and the circuit breaker. The ground fault sensing device is a current transformer that encircles all the phase conductors and the neutral conductor if present. The circuit breaker is a device that is designed to interrupt the flow of electricity in the event of a fault. The selection of a ground fault protection relay depends on several factors, including the size of the electrical system, the voltage level, the type of equipment being protected, and the desired level of protection. It's important to consult with a qualified electrical engineer to determine the appropriate ground fault protection relay for the specific application. The installation of a ground fault protection relay should be performed by a qualified electrician in accordance with the NEC and the manufacturer's instructions. It's important to ensure that the relay is properly grounded and that all connections are tight. After the ground fault protection relay is installed, it should be tested to verify that it is operating correctly. The testing should be performed in accordance with the manufacturer's instructions. Regular maintenance and testing of the ground fault protection relay are essential to ensure that it continues to operate correctly. The frequency of maintenance and testing will depend on the specific application and the manufacturer's recommendations. Typical maintenance procedures include visual inspection of the equipment, tightening of connections, and testing of the relay's functionality.